Hello class. Today we are going to kind of introduce solids for you. Now solids isn't anything super crazy. When they say solids, they're really talking about three-dimensional shapes. So 3D, you wear the 3D glasses at the movie theater. A polyhedron is a solid, it's 3D. It's bounded by faces that are polygons. And what that means is that all the sides are flat surfaces. Okay, so your polygons have, straight sides, no curves, and they're all flat. An edge is the line segment formed by the intersection of two faces. Face being a side. So if you were thinking of maybe a dice where the side with the 1 on it and the side with the 2 meet, that forms that edge. It's exactly what you would think of. A vertex is a point where 3 or more edges meet. You can almost kind of think of it as a corner. Again, if you were thinking of a dice where 3 faces or 3 flat sides met, that corner would be a vertex. A regular polyhedron, regular meaning all the faces are congruent, regular polygons. And by regular, that means all of the angles are congruent and all of the sides are congruent. Equiangular, equilateral, that's what regular means. A convex polyhedron, any 2 surface points can be connected by a segment entirely inside or on the polyhedron. We've got some pictures of that we'll show you in a second. A cross section, well, it's the intersection of a plane and a solid, and it kind of looks like a piece of paper is kind of slicing your 3D shape in half. And again, we've got pictures of that later. So those are kind of parts of a solid that we're going to be dealing with today. We also have these crazy things called platonic solids. And page 721 in your book has really, really cool pictures of those. I'm going to circle that because it's important. Definitely take a look at those tonight. They're kind of special shapes. There's the tetrahedron. It always has 4 faces, 4 vertices, and 6 edges. A cube you see all the time. It has 6 faces, 8 vertices, 12 edges. An octahedron has 8 faces, 6 vertices, 12 edges. A dodecahedron has 12 faces, 20 vertices, 30 edges. An icosahedron has 20 faces, 12 vertices, and 30 edges. You do not have to memorize those combinations, but they're just really cool, special solids that I think you should probably check them out tonight. What you will need to know, and he gets a little snuck in here, is Euler's theorem. I'm going to highlight him in there. Euler's theorem says if you take your faces plus your vertices, it should always equal your edges plus 2. And they've kind of made it into this cute little formula on the back end. F for faces, V for vertices, E for edges. So Euler's theorem, it's a way to kind of come up with, well, how many parts should you have? And we'll use that tonight for examples. So lots of vocabulary. Let's see what we're going to do here. So first thing, example 1, decide whether the solid is a polyhedron. So using your vocab. And then we need to explain. If it is, give the number of faces, vertices, and edges. Well, in picture A, it kind of looks like a box, if you're packing a package to send in the mail. Well, is it a polyhedron? Yes, it is. And the reason we know that is because all of those faces are polygons. The top and bottom are rectangles. That's a polygon. Flat sides, left, right, front, back, all flat faces. Well, when you're itemizing faces then, well, you have 1 top, 2 bottom, 3 left, 4 right, 5 front, and 6 back. There are 6 faces or sides to that box. Vertices Well, the vertices are the corners. If you go up in here, we've got, I'm going to start on the top front. 1, 2, 3, 4. You switch down to the bottom. 5, 6, 7, 8. There are 8 vertices or corners, and that's kind of the points of your picture. The edges, well, those are pretty much on the picture representation. It's the lines in there. So if you go through, I see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 edges. Okay, and those are the lines in the picture again. So pretty easy. You're just kind of going through and counting shapes. Part B, totally different 3D shape. Is this one a polyhedron? This one is going to be no. And the reason is some of those edges are rounded. Kind of looks like there's a half a circle shoved on the front of that face, and that doesn't count. We need all flat, straight sides. On the back, doing some more vocabulary, they want to know an example too. Is the dodecahedron convex? Is it regular? And explain. So there's really 2 questions in there. We'll say 1 and 2. First of all, in shape A, is that dodecahedron, convex? And this one, yes it is. Okay, the reason being, all of the segments between the vertices are inside or on the shape. In figure B, okay, is that one convex? In B, this one is going to be no. If I took my top 2 vertexes and I connect them, that line is going to go through that outside, exterior space. So that is why that one is not convex. I'm going to say that I can connect outside of the figure. Okay, so that's the convex stuff. Let's talk about being regular. If it's regular, all the angles, all the edges, all of that stuff is going to be equal or congruent, equal angular, equilateral. So on figure A, is that one regular? No. The biggest thing I'm noticing, the top are squares, and then the sides are almost like they're trapezoids. They're definitely not the same shape, so right away it can't be regular. So I'm going to say some faces are squares and others trapezoids. Okay, so when you explain, be specific, put the mix of shapes in there. Part shape B, is this one regular? This one's also going to be a no. I see in there some rectangles and I see some squares. Okay, the rectangles are more like the longer sides, but if you look at the very tip tops, those are squares. Again, you have a mix of shapes, so no, it is not regular. Example 3 says, describe the cross section. Now I'm going to go in there and highlight it. What we have in figure A is a cube, and it's being slashed almost, but it looks like this piece of paper is being shoved through it. Where it crisscrosses inside that shape, where it's kind of cutting through it, it's forming a shape. I'm highlighting it here in green. And when you look at that shape, it kind of looks like a rectangle. So when you go to describe your cross section, you're going to say rectangle. So if you kind of highlight the shape where it cuts through, that kind of helps. On part B, I have another cube. We're putting the paper, slicing through it in a different position. If I highlight those edges where it's slicing through here, well, I've got 4-sided shape, and the sides are kind of scooching in on itself, so I'm going to say the best name there looks closest to a trapezoid. Okay, so you're just really naming shapes when you're naming the cross section. Now down in example 4, this is where we're going to use Euler's theorem. They say calculate the number of vertices of the solid using the given information. So in part A, we have a shape with 10 faces. 4 of them are triangles, 1 is a square, 4 are hexagons, and 1 is an octagon. So what they're really giving us, if we have this shape, we can figure out the edges. So I'm going to itemize here. They say there's 4 triangles. Well, a triangle has 3 sides. So 4 3-sided shapes is a total of 12 edges. There is 1 square. 1 square has 4 sides. That's a total of 4 edges. There are 4 hexagons. A hexagon has 6 sides. 4 times 6 is 24 edges. There is 1 octagon. 1 octagon that has 8 sides. That's a total of 8 total edges. So when you add them all up, 12 plus 4 plus 24 plus 8, that is 48 edges. The problem with that is that's not the actual true edge total, because when you take all these flat individual triangles and squares, when you start to piece it together and glue it together to make it look 3D, the edges, well, you got to glue it to another edge of a different shape. So they're sharing those edges. So the trick is you have to actually divide it by 2, and there's actually 24 total edges. Okay, so the trick is add them all up, divide by 2. Then we get to use Euler's theorem here. Faces plus vertices should equal edges plus 2. We know from they gave us that there are 10 faces plus, well, the vertices we're going to solve for, so I'm going to keep that V. We just found 24 edges plus 2. If we simplify, we now have 10 plus V equals 26. And when you subtract 10 from both sides, you are left with a total of 16 vertices. And that is the last thing, that's what they wanted us to find, total of vertices. So it's kind of a process. You have to organize, itemize, put it into Euler's formula, and solve for V. So let's do it with a totally different shape. This time we have 11 faces. 5 of them are quadrilaterals, and 6 of them are pentagons. So we don't have quite the variety this time. If we have 5 quadrilaterals, that's 5 shapes with 4 sides each. That's a total of 20. If there are 6 pentagons, that's 6 sides. Pentagons have 5 sides. So 6 5-sided shapes, that's a total of 30. Overall, that is 50 edges total. Well, remember, when you put those shapes together and start gluing the sides to make it look 3D, they're sharing the sides. So our trick is we divide that by half, and there's actually 25 edges. When I go to put this in Euler's formula, F plus V equals E plus 2. We have 11 faces, V we're solving for, 25 edges plus 2. If we simplify on the right, we actually are equal to 27. And when you divide by 11, your vertices equals 16. Just to point this out, these 2 examples happen to be 16. You can get different answers, so don't think it's always going to work out to be 16. You just have these 2 that happen to go. So for homework tonight, you're playing around with a little bit of vocabulary, kind of looking at figures, naming parts, and then you've got itemizing with this Euler's theorem.